Hello, I'm Andy. This is CB. This is how does Git actually work. I've got some questions that I'm going to ask CB, but really we're hoping that you ask questions so that we can answer the things you're interested in. The idea of this is to try and get a handle on not just how do you use Git, but why do the commands look the way they look. And in order to get into that, we're going to get into actually how does Git work, what does it do. I'm also going to be asking you questions about Git. I'm going to start with one of them. So my first question to you is, what is the name of the directory that Git uses to store stuff inside your directory? .git, correct. Some of the questions are going to be harder than that. So let's start with a question for me.
OK.
So move us on. My first question for CB is, what does Git init do?
Well, I'm glad you asked me that. So far, this is going to plan. So Git init is generally what you use to create a new Git repository. And there are a number of options, but the kind of like the traditional one is to just generate a local repository which has your working code in that you want to store. So I have here pre-prepared a little Docker container, just so I don't ruin my entire machine. And I'm going to create a repository. And as you can see, this isn't actually a Git repository yet, because there's absolutely nothing in here. So what Git init does is something like this.
OK, thanks. Yeah.
There it is. You've got a .git directory now. Now, unfortunately, still not actually a Git repository, because you need a few crucial things. You need somewhere for Git to store its objects. And so objects in Git, they're blobs, like the contents of your files, trees, which are like folders, commits, which record your history, and possibly tags, if you like tagging stuff. I'm also going to need somewhere for my refs. So refs are things like branches and tags. OK, I've used tags in two sense. So tag object only has a useful name if you actually tag it with a reference. And then you can kind of like get to it easily. So I've got somewhere to store my objects. I've got somewhere to store my refs. I'm going to set up a config just with some basic stuff. I'm just going to set some basic core stuff, like a repository. The embarrassing thing is this probably works if I misspell it. Despite over a decade of development, we're still on repository format version nil. So lots of things that have changed format in Git, like the index have got their own version. But basically, the base repository has stayed the same so far. My file system supports file mode. This is not going to be a bare repository. And I'm going to log all ref updates for posterity. OK, cool. So I have almost everything I need here. Yeah, no, it's still not Git repository. I've got to have one other thing, one other really crucial thing. I need to know where my head is. And I'm going to say that I'm on master first. So this file is what's known as a symbolic reference. For a while, Git just used file system symbolic references for things like branches. But so that it can work on systems without symbolic links, and also for a bit more flexibility, it uses these like these link files. OK, so I now have a head. And now I have a working repository. So if you go back to the slides, maybe. So there are a couple of other things that you might get if you actually call Git init that I haven't bothered with, because they're totally optional. You might have a description. This is really only visibly used if you serve your Git repository via one of the really ancient and venerable mechanisms like
GitWeb?
There's that cgit online thing. And I think if you use Git InstaWeb, which starts up a little mini web server to serve your stuff, it's sort of the equivalent of what you type in the description on GitHub and things, but they probably don't use the .git description. I don't know. And also there are hooks, so you can set up your hooks, but if you don't have any hooks, you don't need them. And git info exclude is your like local .git ignore file. So is anybody not familiar with .git ignore and wants to know about it? Okay, cool. So
this, what's on this slide is what I found out yesterday when I just did a git init in an empty directory. So interestingly, we didn't get, when I ran git init, I didn't get a refs or a objects directory. Can you explain that? Maybe you don't need them.
I assumed it was just off the bottom file. Do you not get the objects until you first add? Maybe you don't get an object file until you first add stuff.
So I'm not sure exactly what it was that made Git decide that your thing wasn't a repository until maybe it was head.
You definitely need a head, and I think you need a config. It's sensible to have a config because otherwise some of those core things need to be set up, like file mode is kind of quite important for that. So
cool. So my next question to you is what is the head? Anyone? The branch you're on. Is that a correct answer? It's something like that, isn't it? It's kind of where you are. Right?
So, yeah, the head ref is, it's difficult to come up with like a single description because it has two slightly different consequences depending on whether you're on a bare repository or not. So it's basically the current state of the repository in terms of what commit you're looking at, or possibly what branch you're on, and therefore what commit. So it points to the commit that it points to the commit that's going to be the next parent of the thing that you actually commit. In a repository that you clone, it tells you what the default branch you're going to get checked out initially is, if any. We made a ref file, so we actually had it pointing at another ref. And because that ref has a name and was a branch, it means you're on a branch. But it could also just point at a raw commit. And in that case, you're in this detached head state, which is the source of many of Git's most popular error messages, or least popular error messages, depending on whether what your mood is, like what you're looking for. So, it's where you are.
My understanding of what the head means to me, without knowing all of the details, is that it's often it's the branch that you're on, and if it is the branch that you're on, it has this magic behavior that the head gets updated to the tip of that branch if you do more commits on that branch. Whereas if it's pointing at just a random commit, the magic behavior goes away and you remain detached even if you make some commits. Am I right?
Yeah, so if you call any user command that moves you onto a branch, or that basically checkout is the only one. If you check out something that's a reference that's under ref/heads, then head will become a symbolic reference to that branch, and then your commit operations actually happen on that branch, and that ref file just stays the same. If you check out something else, so a ref that isn't under heads, so refs tags or something, it doesn't become a symbolic ref. It becomes just an actual reference to a commit ID. We can show this later.
Yeah, show that.
And then when you next commit, the head file itself gets updated, and then no other branch kind of gets updated. So if you check out a tag and then you commit on top of that, you're not on that tag. That tag is just something that you use to identify what commit you checked out. Cool. Shall we move on? Is that?
Yes.
Yeah. Does anyone want some other question that they feel would kind of fit in here?
Does anyone want to ask a question about any of the many things we just said that you didn't understand? Did anyone understand everything we just said? There was a nod.
That's enough.
Cool. So what happens when I git add?
Well, let's get a file to add. I'm going to call it main.cc. This is kind of like embarrassing because I'm not going to bother to compile it. So I'm probably going to get something that doesn't work or isn't C++20 or something deeply untrendy.
When I did this, I did it in Python. It's fewer characters.
I don't know, might compile, might not. So what does git add actually do? Well, the first thing it does is it basically copies this object into your repository, but it doesn't quite do that raw. First of all, we need to work out what ID this object has, and if I have a quick look at the directory, I can see this is a 69-byte file. It's going to be a blob, which is just a normal file, as opposed to any of the other Git sort of objects. So I'm going to make the kind of...
So I guess the first thing to say here is that that Git doesn't know about this file at all yet. So there's nothing
it doesn't know about this file at all.
There's nothing in .git referring to this file yet.
So it's a blob, 69 length, and then the end of the header is a 0 byte. And then I'm going to cat the contents of that file, and I'm going to pipe that to SHA-1 sum. And SHA-1 is the famous, now broken, reasonably broken hashing algorithm that's the core for all of Git at the moment. But Git is moving to SHA-256, and that's an ongoing effort. It will not, I believe, change the repository format. Not quite sure about this, but I believe it's one of these incremental things that will just work. I mean, there's been a lot of development effort, and I'm not responsible for any of it, but lots of great people are. And so it will be a reasonably seamless change as people decide when their clone of a particular repository, when they want to move that to SHA-256. And initially, if your server's using a different hash algorithm from yours, there will be some performance overhead. There'll be lots of internal mapping structures that kind of mitigate that. And then eventually, everyone moves to SHA-256, and the world will be a happy place. So anyway, so the ID of this object is not the SHA-1 sum of the contents of the file on its own, but we have this little header that says what type of file and how big it is, and then we cat the contents of the file, and then we get the ID of this file.
So just to explain what that command that CB typed does, you better correct me if I'm wrong, but it makes a new, well no, it prints to the console that phrase, blob69 and then a null. Then it prints the contents of main.cc, and then all of that gets piped into SHA-1 sum, which hashes it and prints out the hash of what you put in.
And if I change the case of just one letter in that, obviously I get a completely different hash. And I'm suddenly really reassured, because I did this in a demo just to make sure I got the same ID, and I got something starting with 1CBD, and just now I got a completely different hash, and I thought, have I messed it up? And then I thought, you know what, I think I typed world with a lowercase w, and I did, so I'm feeling pretty good now, I'm feeling pretty good. So now I know what the ID of this object is, I can now write it into my Git's object directory. But the way Git does this is it creates one of 256 directories based on the first 2 digits of the hash. And then, so is anybody familiar with the pigz command?
No.
No, OK, didn't think so. It took me a while to find this. So objects that Git stores in the repository are lightly compressed with just zlib compression. So it's basically gzip, but without the header that gzip would give you. And pigz is one thing that does this. So if I do pipe .git/object/1c/
Oh, yeah, that was one of my questions, actually. So the name doesn't get the 1c included in it, which I was expecting it to, which confused me. So just to explain a little bit about what's going on. So that command prints out the same stuff that we just had before, but instead of hashing it, we zip it and then put it into a file with that name. The reason that these names might be good is because it's extremely unlikely that a file with different contents is going to end up with the same name when we use this scheme. So, except when you deliberately do it, which you can do, it's unlikely to happen. So we're likely to be able to find files easily and not have them clash with each other.
So as you can see, we have this compressed object, which is 85 bytes.
Cool.
I mean, to be fair, we put a 8-byte header on it, so it's only gained about a dozen bytes. But yeah, so compression like this is obviously kind of like a win when it's a win for compression. For a really small file like this, doesn't matter so much. So I've got an object in there. Does Git really believe that I've got this correct? Oh, actually, I forgot something. I should really have made this non-writable. I think in rehearsals I had a umask in there. So objects are immutable because they're content addressable storage is the buzzword. So it's defined by its contents. You can't change a file. You can create a new file. It'll have a different ID because obviously when you hash it, it'll have a different ID.
So this is effective. Like when people talk about the database that Git's based on, this is effectively the database that you can look up. If you know the contents, you can find the file. Why would you want to do that?
So everybody familiar with Git fsck? So Git fsck comes from the Unix disk command fsck, and it basically checks a whole lot of things in your repository and finds stuff that's out of whack in some reason. So here, notice. So a notice is not that important. You might be interested to know. Head points to an unborn branch.
What's an unborn branch?
So I created that ref file, that git ref, and called head, and I said I'm going to check out master, ref's head master. Well, there isn't actually a branch called master yet. Yeah, that's basically what that notice is saying. But as soon as I make a commit, it'll create a commit that doesn't have a parent and point master at that. So head points to an unborn branch. It does point to a branch. That branch just doesn't exist yet. But as soon as I make a commit, that branch will start to exist.
So Git looks at what's in head, sees that it's a magic branch-like thing, and knows that it should have magic branch behavior, which in this case is to create a new branch.
Yeah.
Right, that's cool.
Not quite sure what no default references means, actually, to be brutally honest. I suspect
Anyone?
I suspect it's because I didn't even create a heads or a tags directory in refs. Or, yeah, it's probably because refs is entirely blank. It would be possible to have some stuff in there and still have head pointing to an unborn branch. So, yeah, we could try that later. And the other thing is I've got a dangling blob.
It doesn't sound good.
It's fine. So, when I create an object in Git's database, there's kind of like no way to find that object unless I've already got the contents of that object. So that's the only way I could find that ID, unless it's referred to by something else. So I don't have anything that refers to this object, is basically what this is saying. So there's kind of like no way to find it. So at some point, if I was to run git gc, provided this object was old enough, Git would go, well, there's nothing referring to this. I can tidy this up. So it's one way of kind of getting rid of cruft.
Okay, so Git GC stands for garbage collect, and it means delete the dangling blobs, right? Basically,
yeah.
Possibly some other things.
Git GC does a number of things. It prunes dangling objects that are old enough. And it also cleans up the ref logs. So I turned on that config file called logall ref updates. So when you make a commit and Git moves a branch pointer forward to the new commit, it also keeps a log of where all of the references used to be over time. And you can go back and see where master was 5 minutes ago, last week, or 100 steps ago. And so that ref log is one of the things that might refer to this dangling blob. So particularly if you amend a commit or you do some sort of a rebase, you can kind of lose connectivity to commits from the main branch history, but you could still find them in the ref log, sort of old versions of that branch. And eventually, those ref logs don't stay around forever. I think it's 30 or 90 days, the default, one of these, like a month or a few months. And after that, Git GC will kind of clean out those old ref logs. Stuff will end up dangling because it's no longer referred to. It'll clean up those objects. And you can do things like you can give GC a number of options, and it's got a number of subcommands that it calls. So prune all ref, I think it's prune refs. There's an option, prune all refs, that you can get. You can get kind of like detailed and technical, and you almost never need to do that unless you're particularly trying to work out if your pack file's got everything you thought was in it or how much space stuff. Yeah, we can do fun stuff like this. I've got the man pages available. I don't have to know everything.
Reading the man pages on the train up here, and I was reading about, there's prune all refs and a couple of others that essentially just get rid of stuff that is no longer needed, and because we think it's old enough that you probably really meant not to need it.
Yeah. So we're about halfway through what Git add does.
Right. Another tip, just general Git usage tip. If you rebase and everything's gone, and you don't know where you are or what's going on, the objects are still in the database. There's still files like this, which have got your code in them, even though you've lost it all. And there are commands that can grep through those objects and get them back and turn them into commits that Git actually knows about, so you can effectively find them again. So all is not lost, but only if you made a commit with that stuff in. So do that.
Okay, so here's some advice. If you think you've lost something, but you thought you might have ever Git added it, stop. Do not touch the repository. And this is just the same as pretty much any other backup story. It's like, stop, stay away, do not touch anything. Take a read-only copy with base tools, give the copy to an expert, and they will tell you what they can recover from it. But yeah, sometimes you can find stuff. Sometimes it's hard work. But yes. But some commands can trigger an automatic garbage collection. And so this is why you don't want to kind of do any work that's unnecessary in your repository if you think you've made a mistake and you think there's something important you might be able to recover. Cool. So we're halfway through Git add. We've added this object to our database, but it's totally unreferenced. So I now want to add it to Git's index, which is the second stage of Git add. And so what I do, obviously, is I look at the documentation for the index, which is available in Git's man pages. And you'll discover it's kind of like a really awkward, annoying binary format. So I'm not actually going to do that. I'm just going to cheat and use a low-level index manipulation tool called Git update index. I'm going to do an add operation, and I'm going to tell Git to put a file, non-executable file, for which the secret code is obviously this. That top 1 bit, that means regular file, and the bottom 644 are Unix permissions. There are only 2 allowed Unix permissions, then that's 644 and 755. Git doesn't track owner or group, just the kind of executability. And then I'm going to use my blob reference, and it's main.cc is going to be the name of the file. Cool, excellent.
Okay, so let's talk a bit about what the index is. So I'm going to try and say what I think the index is, and then you're going to correct me, okay?
Let's say spot the index.
So the index is like a place where you do some work, where you're preparing a commit. That's how you would think about it when you're doing stuff normally. So if you've got files that you're getting ready, you're going to make them into a commit, you do git add on those files. Whether or not they already exist in the repository, you still use the word git add. When you do git add, it puts them into this place, which means that these are ready to get committed. And then when I do a git commit, everything that's been put in there gets turned into an actual commit. That's the kind of day-to-day, this is what the index is. But really what the index is like an optimization that means that Git doesn't have to search through all your files as often as it otherwise would, because it can just look at the modified time on your files and check whether they've been modified since it updated its index, right?
Yeah. So from a user perspective, the index is the staging area. And that's, for most users, it's pretty much all you need to kind of interact with it in a useful way. Unfortunately, it is also an implementation detail. So it's also known as the cache. And it's basically like a stat cache. And Git can use it to optimize lots of operations like status and stuff. So actually, let's have a look at the index. So you'll notice there's a brand new file as of however whatever timestamp I ran that update index command. And x1z.git/index.
What's that? What's OD?
OD is like a hex dump, but it's more universally available. So,
cool.
I'm glad you asked. So this is the index. It's like a binary format file. You may be able to spot a few interesting aspects. So the first aspect is that there's a signature, which is DIRC. Does anybody know what DIRC stands for? Dir cache, so directory cache. Back in the day, it wasn't the .git folder. It was actually called .dir cache. And this was kind of like the index of .dir cache. There's a large number of zeros, which I'm going to magically fill in a moment. And then you'll see some interesting stuff. Oh, I've got a boom mic. I can move around. So A1, A4, there's a bit set here which says, no, I'd have to look it up now. But 1A4 is actually 644 octal into hex. Octal into hex is like one of the really awkward ones. You think it should be really easy, but it's like groups of 3 to groups of 4, so it's not that easy. More zeros. You may recognize some hex digits from earlier in the talk. So 1C, BD, AD, all the way down to 7D. So that's a SHA-1 sum. 07. Do you know how many bytes in main.cc? Oh yeah, 7. And then oh yeah, M8. There's cheat sheets over here. Main.cc, and then there's some other stuff.
So hold on. So this is the file name, but in
that's what you were pointing to, the badad B5 thing.
That's the beginning of the
file name. That's the SHA-1 ID, which is
which
the file name on disk.
Which happens to be translatable into the file name if you translate these bytes into ASCII representation of bytes.
And then this is the file name actually in the checked out directory.
That's the name that we want it to have when we check it out.
Cool.
Simples.
So now I can run something like Git Status, and you'll see that we're in exactly the state after running Git add, but much more labored and more fun.
I feel like I've seen a way of printing out the index in a way that's more readable. Like, is there an ls files or something?
So I was just going to do this again. And here's something interesting. All I've run is Git Status, a totally read-only command, and lots of stuff has happened. Yeah, what you'll notice if I run git ls files. So actually, let's remove the indexes. Yeah, you can recreate the index at any time. There's if you.
It's fine.
So here's the kind of like the change that Git Status caused. So when I just do a low-level update index, I told you that it was a stat cache. But when I just kind of said, here's the cache info, this is the blob that I want to stage at this particular path. When I do update index with that, I haven't told it to look on disk. So it doesn't look on disk. So it doesn't have any stat information on disk to store there. But when I do Git Status, what I'm asking it to say is, has anything changed on disk? And what it'll do is look at the index and go, this file should be on disk, but there's no stat cache information. I'll stat the file. Oh, yes, the file is there. It'll then also read the file to see what the contents of the file are on disk and go, oh, yes, the file on disk matches what is in the index. So I'll update the index and record all of the stat information in there.
I'm going to try and translate some of that into human. So the when we ran update index, we were adding. You can think of index as just a list of all the files that Git knows about, and how to find them in this database, which is the files with the hash names. So running update index just added a line saying this file exists, and then ls files just prints out what's in the index in a friendly way. So ls files just said, I know about this file, and it was never modified, or whatever 0 means. Then when we run git status, it checks the actual modified time Of the blob file?
Of the file on disk. So there's
The one with the hash for a name?
no.
No, the one in the
file,
working tree.
One in the working tree. So the stat cache is all about checking that your working tree matches what's in the index.
Okay. So now Git status, which we think of as not having any effect, actually does have an effect on the index file because it's just a cache. And now our friendly view of what's in the index shows correct information, or recently correct information about the modified time of that file. Because stat, when CB says stat, they mean modified time and stuff like that, yes.
If you delete the index, what does status do?
If you delete the index, what does status do? We can do that.
That's a good idea. I was just going to see if I could get. Is there a raw date time option to stat? I'm sure I. No. Well, I could do help. I'll give up in 3 more things.
Meanwhile, I'll ask you your next question. So your next question is, where does the name Git come from? Why is it called Git? So the answer is, doesn't Linus name all software after himself? That is something that he said about the name Git, but I think it's retrofitted. I think the actual reason why it's called Git is because it's a 3-letter word that is memorable. I think that's what he said. And also, presumably, because he thinks it's funny.
And it's quite easy to type, which is nice. So yeah, if you delete the index, then basically you have nothing staged. So if I'm on my initial commit, I just have untracked files. If, however, I'd actually made a commit, it would look like I wanted to delete everything. We should make a commit at some point, shouldn't we?
Hold on. So you deleted the index, and now it's. So is that any different from when we had something in the index?
Yes. Now I'm in the index. I have changes to commit.
Okay. So that's done effect. That was what it would look like if we'd done git add, which is good because we're trying to do git add, right?
We're at the state of git add. Are we back to the slides yet, or?
Have we finished git add?
Yeah, this is git add. We've done git add, and then we've redone it a few times, just for the interests of.
So what git add does is make sure that this version of this object is somewhere in the database, and that this object is mentioned in the index.
You didn't write the same Hello World program as I did.
No, as I said, I wrote mine in Python, but it's okay because it's Python 3. Yeah.
Python 3D.
Say again, sorry?
If I do a git add and then I just do a git reset, I can still find the file even if I say, okay, I installed it.
Okay, so if I do a git add, then I do a git reset, will the object still be in the database?
Yeah, brilliant question. So what I didn't do is after a git add, if I do git fsek, you'll see that there's no longer that dangling blob. So that thing in the Git database that is now referred to by something, and what it's referred to by is the index. If I remove the index, I'm completely removing people's fear of doing rm.git/index, and somebody's going to get in trouble for that one day. If I now do git fsek, it'll say I've got a dangling blob. So yes, that object still isn't there. It's now ripe to be reaped or garbage collected.
If you do git gc now, it won't go because it's too new. Is that right? Or?
This is true.
But if it was old, it would go. Yeah.
If you were to delete main.cc now, could you retrieve it?
If you were to delete main.cc now, could you retrieve it?
I did something in the background that may have changed the answer to that question.
Let's do things in the right order now.
Okay, so what I did in the background is, while you were asking the question, I did a git gc prune equals now, and this turns off the safety valves of let's leave things around just in case, and goes kind of quite brutal. And checking object directories, one of those directories it will have found was this thing with 1C. It will have found an object file in there. It'll gone, is that newer than now? And actually, it's a few minutes ago, and a few moments ago is older than now. So whoop, it's gone. So you couldn't do that now. However,
so this is the command to type if you insulted your boss in a comment and then thought better of it, and it's still in the object directory.
So the question was, if I did an add and then a reset, so I've done an add, I should probably use the normal commands. So
Well, actual git add. Have you even got it installed?
yeah, 'cause this is Git version 2.20 point something. So if I do git reset, which I could do.
Do you need to say where to reset to? Do you have anywhere to reset to?
It doesn't matter. Git reset kind of just works for any situation. It's
One of my questions ought to be, why are there so many different meanings of git reset? We'll get to that maybe.
so as you can see, it's not in the index. Sorry.
Hang on.
As you can see, it's not in the index. There's nothing there. Sorry. I realised we're kind of quite low down. If it's, can you see at the back? I see a few craned neck. I might just reduce the height of this a little bit and move the thing up.
What is all the stuff that is in the index then, if there are no files in it?
So basically, that's just like a header. So this is, we're actually using version 2 of the index. It's true. Mm-hmm. I could prove it. So there's a header, and I believe there's actually a SHA-1 sum in there. So for consistency, or just so you can check whether it's valid, I think there are enough bytes. I think it's basically just header.
Looks a bit SHA-1 sum.
Yeah. Does that look plausible? It may be that there is a SHA-1 sum check in there. It may only be created when you've actually got entries, so I'm not quite sure.
Okay, so you can ignore that. That's what I take away from that.
Let's live dangerously.
So you've just changed the index version to 4. Is there such an index version?
Trust me.
So does that represent something useful, or have you just made up the number 4?
So there are, it's got support for some extensions, and
but it's not used by default.
It's not used by default, no. So
don't care.
I'm afraid I don't have good information on those extensions at the moment, but
cool. I really don't know why you muddied the water.
When you've got really big repositories, it might be part of the split index stuff that's coming up. I'm not sure.
That's another split index and nothing I read.
Have we answered your question of like when you git add and reset, can you find it back? And the answer is yes, because it's now a dangling blob. So for a while, it's accessible.
Right. So git reset did the same thing.
Yeah, if you get reset, even if you do GC, as long as it's sufficiently recent, you can still find the blob.
So it had the same effect as deleting the file? No, it also removed it from the index.
No, we didn't touch the working tree at all. We were just removing the index.
Only removed it from the index.
Yeah. Okay, cool. Should we make a commit?
Okay. No, not yet.
No. Oh.
Other questions completely separate or related to that? Yeah, is there a git command for looking at what's in the index without looking at the hex? Yeah, well, there's that ls files, right?
Yeah.
That is the index, right? Basically?
Git ls files is basically showing you what's in the index, and -s is for staged, so that's showing you what's staged. The non-debug version is just showing you file mode, object ID, and should I talk about the 0?
I don't know. Let's answer the question. I don't know what the 0 is, so I don't know how to answer. So this is the view that I was expecting of the index. This is what I've seen before. So this is how I think of what the index is like, right? It's not really, it's that binary thing, but essentially one line per thing that Git knows about. Go on then, tell us about the 0.
The 0 means it's this is stage 0 of the index. So the index can have up to 4 stages. And when you add stuff or check stuff out, everything's always in stage 0.
And it's to do with merging, right?
Yes. If you were ever in a situation where you're merging stuff and it didn't automatically merge, you may find things in one of stages 1, 2, or 3, or several of those stages, but not in stage 0. And resolving a merge conflict is all about adding something to stage 0 instead of those other slots in the index.
So we don't have an example of merging prepared, but if we get to it, we might show
we could do that.
a merge conflict.
I mean, we could do anything. Why didn't you book us a double slot? I mean,
Yeah, well.
I thought we were going to I thought we might run out of stuff, but like, yeah, there's lots to get.
Cool. So any other questions, or we'll move? Yeah, one more.
Just to be sure, that when I push Git repo, does the index get copied, or?
When I push the repo, does the index get copied, or how does the index interact with pushing to remote?
No. So a Git index is tied to a working tree. Yeah, I think that kind of makes it as simple as possible. So the index is local to your local repository. You only have an index if you've got a non-bare repository. And when you push, the only things that are transferred are commits, tags, and any objects kind of chained off them that the remote side needs.
Yeah, so there's two ways of thinking about the index we've already talked about. One is it's my staging area where I prepare commits, and the other is that it's Git's cache of the metadata about files in my working tree. So both of those are related to my local working tree, not the real repository history of stuff, commits.
Is anybody familiar with the git worktree command?
I was going to ask whether anyone knew what a working tree was, given that we've been saying it so much.
No, so it's actually possible to have multiple working trees associated with the same repository. So if you use, so if you've got kind of like a clone of a big repository, and you need to do some sort of bug fix, and you've got stuff checked out, you can, rather than recloning, you can create a work tree from your existing repository and check out a separate branch in a directory alongside it. You can use the git worktree command. Very good command. Thoroughly recommend it if you're in that sort of situation. And each work tree will have its own index, but it shares the object database and configurations about pushing and pulling. So that's why I say the index is tied to your working tree rather than saying it's tied to a particular repository.
So just on what your working tree is, your working tree is the normal source files that you edit, everything outside of the .git directory. Is that correct description?
Yeah.
It's your actual files. And that's what, when we say working tree, we mean your actual files. Right, what's the next question? Oh, we've done this. We've done this, yeah. So my description, sorry, go back, CB. So when there's a Git repo that if you ask me on Twitter, I can send you the link to. When I tried out these commands on a very small repository. When I tried out git add, what happened was we got a new file called index, which we now know why, and we got a new file in the object database, and we now know why, right? So now we understand why those files appeared, right? Okay, next question.
Yes, it should.
Oh, I think
You
that's a
must have
typo,
optimized
sorry,
it.
yeah, sorry.
It's been optimized for the slides.
Yeah. Yeah, you may find more optimizations. Okay, so what is a commit?
A commit is a tree and some metadata. Well, actually, the tree is part of the metadata. A commit is some metadata. Is that too simple? That's too simple.
Let's just leave it at that. So this is what happened when I made a commit. So maybe we go through some of these things and you explain what they mean. So something happened to the index, something changed in the index. Also, this file appeared, which I kind of assume isn't that important. This commit edit message. Also, this logs directory appeared, and something called head in there appeared. Also, some ref stuff appeared inside logs, and all this looks to me like maybe I should ignore it because it looks similar to other stuff like this. So this thing which ends with master, which so it looks like a branch to me, appeared, and all the other stuff that was there, and some more objects appeared. Can you just explain all that for me, please?
Yes, I can. So, to be honest, the only thing I can't explain is why the index updated. Oh, yes, I can, actually. It's an optimization. So the thing is, the index does update quite often if stuff has changed. So I was kind of wondering, maybe the timestamp wasn't up to date. Maybe you haven't run Git Status yet, so it has the same effect as Git Status. But actually, what I think probably happened is that behind the scenes, you probably created a a tree object. And then the index, it's a bit more complicated than we've said before. The index also contains some extensions, and one of those is it actually caches tree objects for your working tree. So it probably wrote
remind us what a tree is.
Sorry?
Remind us what a tree is.
So a tree is Git's representation of a folder on disk or a directory on disk. Because basically it contains, I mean, it looks in some ways a bit like Git's index. It contains path names, not with any slashes, only one level of path names, and an associated object, which could be another tree or it could be a blob, which is just a file on disk.
Okay, so some change was made in the index, probably because it's now tracking a tree.
Probably cached a tree that it created.
And it wasn't tracking that tree before.
Yep. Commit edit message. So I don't know, did you run it with -m, or did you kind of let a text editor fiddle with it?
-m.
-m, okay. So pretty much whichever way you do, Git creates a temporary file with the commit message. Normally, it kind of, if you're actually editing your commit message with an editor, it will create that file and let you actually edit that file. And then once you quit the editor, that's what it'll use as the source. Even if you use -m, it kind of creates it, because what might happen is you might have like a commit hook that prevents you from committing something because of some test that's run in your commit hook. And so that you don't lose your 3-paragraph explanation of why you changed uppercase W to lowercase w, it'll save your commit message so that you kind of fix the reason that the commit hook didn't let you commit. Maybe you just add a -f to your commit command line, and you've still got the commit message that you were editing, so that you don't get too frustrated with Git on this particular occasion, at least not for this reason.
So just to explain a couple of things. So when we're saying -m, we're talking about typing git commit and then -m, and then describing that commit without opening the editor. Also, yeah, I've noticed sometimes when something bad happens, the error message will say that I should use that file because it's still got my carefully typed message inside it. So.
Cool.
You don't have to memorize the name, is what I'm getting at.
So the important thing is it's now, in Perl speak, auto-vivified the master branch. Do you speak
There's
Perl?
not enough Perl speak in the conference presentations.
Is there not enough Perl? No, I can't honestly back that one up. So it's created. So this is the actual ref file that tells you where master now is. And as part of this, I said log all ref for updates, and your Git init also did the same thing. So it's updated the log for the master branch, and it's also updated the log for head. So there's actually two things that have updated. Head pretty much updates any time you kind of like commit, reset, check out a new branch. The master branch kind of only updates when master actually moves. So you can see some, particularly if you're doing some sort of an interactive rebase where you make quite a lot of commits, or the tool makes a lot of commits on your behalf, you'll find that like head moves all over the place. But if even if you're rebasing master, you'll only have like one update to master, because internally rebase interactive detaches your head from the branch, does a whole lot of fiddling, and then puts your head back on the branch again. Does sound a bit gruesome, doesn't it?
Okay, so I just want to go over a few things. So head is where you are right now, and that can either point at a branch or a commit, or possibly other things. And we made head, when we manually did an init, we made head point at something which looks suspiciously like this thing. This thing, if I understand right, effectively is the branch called master.
Yes.
Are you happy to accept that?
Let's go with the
I won't use the word
simplification.
effectively so I can get it past CB. So if when you make a branch, what's going to happen is something inside here named after that branch is going to appear. That's just a file. Maybe we could look at it and see what it looks like.
Yeah, so let's make a commit. To make a commit, obviously we need a tree. So let's write the. Oh dear, what happened? Oh, that's exciting, isn't it?
Yes.
Did I recently?
Is your blob dangling?
Oh, did we delete the object? Oh yeah, that's right. That's quite fun. Yeah, so garbage collection has worked. As you can see, there's no that file. So I wonder if Git Yeah, Git FCK would have told me what was wrong. Yeah, I'm missing the blob.
How did you manage to delete the object?
Oh. We did a garbage collection with --prune equals now. I told you it took the safety valve off, didn't I? Or catch, or whatever we're calling it.
But why is it a missing blob if... Oh, did you then re-add it to the index? Okay, okay.
Yes, I re-added to the index, and if you use the raw update index command, it doesn't care if that blob actually exists. It just trusts you that this object ID is a real thing. So now I've put that thing back in there.
So that missing blob thing shouldn't happen to us if we behave, right?
All you have to do is search the world for a file that hashes the right thing after you put that prefix on, and you're good.
Cool.
Fortunately.
Sort of some kind of proof of work.
We're not in a blockchain talk. What have I done? So yes, I've got everything. So now I can make a tree. Write tree is a nice, useful command. It creates a tree out of all of the entries in the index.
Why would you want to do that?
Because when I commit, this is going to be the root of the. Oh, did you just want me to use git commit?
No. I really want you to do. I want you to do this. I just want you to do it really slowly.
So now I have a tree object in my repository. And if you look at what this tree contains, it's a mode, a type, i.e. blob in this case, the ID of that, and then what the name of that in the tree is.
Hold on. What's going on? So git write tree
takes the index
right.
and makes a tree out of it.
Why?
What do you mean, why? That's the whole raison d'etre of git write tree. If you ask git write tree, why did it make tree? It's like, well, you told me to.
Okay, so that's because a commit is everything, like a record of everything that as it currently is at a moment in time, and we're using the index to say this is the thing that I want you to be saying is the thing that happens at that moment in time.
Yeah, so git index is a staging area, and it just links basically blobs to paths or files on disk to paths. But when we create the Git's history, it's nice to have these tree objects. So if you've got a big wide directory tree with lots of stuff, and you only change a file over here, is like the rest of the rest of all of these branches stay the same. Whereas your index, if you created a SHA on some of that index, every time you change each little thing, because it's a big monolithic structure, kind of the whole thing changes. Whereas a tree object contains other trees and other trees, and so when I change this file, most of these trees stay the same, and then the difference in the tree itself can be kind of stored incrementally, and it's not such a big change to keep. It's basically we're translating from an optimization for Git to use to an object model that's better for kind of describing history and doing kind of disk through history, which is why, I mean, in theory, you could write something like Git that just had indexes and trees, and you kind of kept the index without the stats bits in there. But a tree object is basically that.
So write tree actually made an object in the database.
Yep.
And that object.
So I've now got two directories with digits, and you can see 07 was the beginning of. So when I ran write tree, it print the ID of the tree that was created. So 07 9020. What? It was nearly 90210, wasn't it? But
Okay, so that's the object that it made. Can we look at what's in that object?
Yes. So the user readable version is lstree, but you can, of course, no, not that one. And just because I know, I'm going to do tx1z, because there is some binary stuff in here. It's mostly the same, but yeah, for some reason, I mean, this could almost have been a text format, but just for optimization, the ID of the object, so 1CB is actually stored as a as SHA-1 hex, not the ASCII representation of the...
Okay, so write tree made an object which is of type tree.
Yes.
Tree just means something that's a bit like a directory.
Yep.
And
So-
the contents of that is a list of everything in the index with this extra information about it.
So this is like a directory listing. It's got the file name, it's got the type, and then it's got like the contents, but just the ID of the contents, which is going to be another file in the object database. So we've now got 2 objects in our Git database, and now we want to make a commit.
Yes. And then once you've made a commit, we're going to understand why we did that write tree thing, right?
I think this is going to work. I thought we'd be over by now.
CB likes to use the bash foo as well as the git foo.
I'm in a Docker container. I haven't told it who I am. Publish my email address to the internet. Yeah, all right, so I messed up the here document. But, as with all helpful Git commands, it prints me a SHA-1, so I know it's worked.
Right, which is what also happened with write tree. So when we said write tree, what it did was looked at the index, made a object that was a listing of everything in the index, and then printed out the ID of the object it had created. Now we've done commit tree. We gave it the ID of that tree, and we gave it a commit description. It's made another object, and that's the ID of that object. Anyone with me? Some people. Any questions?
Does this tree object contain all the files or just the files which were in the index?
Does this object contain, this tree object contain all the files in the repo or all the files in the index?
So the tree object that the commit refers to contains a list of things at the root of the repository, and those things could be blobs or other trees, but those things in the tree objects are just IDs. They're just SHA-1 IDs, which will point to other objects in the Git repositories. So
So it would be like the listing of the directory.
yes. So
When you say at the root of the repository, do you mean at the root of the working tree or something else?
yeah, the root. The root of the working tree, if the working tree was checked out at that point, if you like.
Yeah. Okay, so it's like...
When you number directories, it would have like object references.
We should. We'll create some directories in a moment. Should we just have a look at the commit first? So
there's one other question before we go on. Someone? Okay.
So commits are a completely textual format, so I won't bother to pipe this to od-t x1z.
So what cat file does is, given the ID of an object in database, which is compressed, right, with gzip compression.
Yes.
It ungzips it and prints it out. Does it do anything else?
It strips off that little header that gets put on the front. So if I did, what's it? Why does DC?
So we've essentially just looked at one of the contents of one of the objects, one of the files in the database, which is a file of type commit because we just created it. And this is what it looks like inside, which ought to look vaguely familiar because this is the kind of information you provide when you make a commit, right?
Git log is basically just a very lightly sanitized version of the raw contents of the commit. So if I did this pigz dcz,
you've got an extra commit 164, right?
So this says this is the object type commit. This is the number of bytes 164. that thing between the 4 and the T is that 0 byte. And the rest is just the contents of the commit object. So yes, there's nothing, only light magic going on here.
Okay, so before I was saying that other thing was a branch, this thing is a commit.
Yes.
Not effectively, it actually is a commit.
Yes.
Although we often talk about commit IDs. We often use the word commit when we mean commit ID. But that's okay.
So creating lots of directories. I'm going to cheat.
Okay, so you just told the index that there is a file in a whole load of directories called main.cc.
Yeah. So yes, I've just used the same blob ID because I happen to have it handy. With
It happens to have the same
main.cc.
contents, so it has the same blob ID.
So just to confirm, in my objects directory, I've only got 3 directories. If I was to kind of like view that recursively, there really are only 3 objects in here. So I've just got that commit object, the tree object, and the file object. I'm now reusing that, or blob. I'm reusing that blob for a file that's just in a deeper nested directory. Git Status will tell me what everything looks like. Does anybody kind of like happy with why this looks like it does? What I'm showing, what's happened? Why I have new file and also deleted?
Any questions? Otherwise, I will try and explain to show that I understand.
Good plan.
Okay, so have we actually made a commit?
We have made a commit.
But it doesn't know about it yet, right? Because I would expect main.cc not to be changed.
Okay, let's fix that.
Is that because we haven't put it on a branch?
Yes, we haven't. We made a commit, but we haven't updated the master branch to put.
All right. So let's move on to that in a second. Let me do what I was originally going to do. So the index knows about 2 files which are not yet in the repository which we consider the head.
Yeah, they're not yet in the head commit, and
Right. So
one of the two reasons is because you don't have a head commit yet.
So the index has got these 2 files in it. They're both considered new files because they're not yet committed somewhere that we know about from where we are. One of them is in the working tree, so that's fine. But this one is not in the working tree, so obviously we've deleted it. Make sense?
I mean, actually, we never created in the first place, but Git doesn't know that.
It does say the stupid content tracker when you open up the man page.
So what was the idea of that commit? Here it is. So I'm just going to fix the fact that we didn't update the master branch to point to this commit.
Okay.
So one obvious change there.
So git update ref, it changes that file, which is called ref/head/master, to point at the ID
of the commit that we just made, yes.
So,
and because head is a reference, it also means that our current commit has been changed too. Cool.
Okay, so when we just run the git commit command, it does all those things. So it does a write tree to make a listing of what's at the top level in the top level directory. It does whatever the other. What was the next thing?
Sorry, I was just preparing our next command.
It does a write tree, then it does
a commit tree, basically. So it just creates a commit object.
It does a write tree, then it makes a commit object, and then it does an update ref on the branch that you're on, assuming you're on a branch, to point at the commit you've just made. Yeah.
Does update ref remove the file committed from the index?
Does update ref remove the file committed from the index? The index doesn't only contain
So this is
files,
where
right?
it is helpful, less helpful to consider it as the index a staging area. So
Yeah.
it's it's almost impossible not to think of a commit as consisting of those files that you changed, because that's how we view commits. We view commits as diff. But actually, a commit is just a link to a tree which contains, recursively, potentially, all of the source that you need to check out the repository at that point. So each commit contains the entire code at that point in the commit. It's not just the changes. And the index also, when you check out a commit or when you make a commit, the index contains references to all of the files in your working tree. So not just the stuff that's changed. But status hides stuff that hasn't changed that isn't interesting. So when you do git status to look at what's staged, it's not showing you what stage that isn't going to cause a change. So this is one of the artifacts of viewing commit history as either a history of complete trees versus a history of what's changed. And this is kind of like where it breaks down a little bit, I guess.
Okay, so I'm quite excited because I feel like I've understood something. So the commit ID is like a hash that tells you, that allows you to recreate the entire state of the working tree at that moment in time. The commit ID is a hash of the contents of that file that was a commit file. That file contains stuff like the author and the description of the commit, and also the hash of the tree object. The tree object is a listing of the top level stuff, like the top directory level in your working tree, and because it's got all the hashes in it, that actually allows you to then trace down into all the other directories. And if any stuff inside there changed, there would be this chain of hashes getting updated all the way through to the commit ID being different. Am I right?
Yes.
Okay, maybe you all got that already. I feel good. Okay, continue.
Okay. So I keep looking at .git/objects, see how many objects are in my Git database. But that's kind of a simplification, because if I'd done git gc, they might be packed away. However, this command will list all of the commands in Git's object database. And it's a command that I'm largely responsible for, because I proposed another command to the Git mailing list, which was resoundingly rejected in terms of just extra options to cat file. And this was just much better performance and stuff anyway. So here we can see we've got a blob, a tree, and a commit. So we've sort of eaten over an hour. We've now got 3 objects, one of each type in our database. Anyway, so just staging this thing with lots of subdirectories hasn't caused lots of trees to spring into existence. However...
Okay, so sorry, is that the contents of the index you just casted?
No, this is cat file, back to all objects, is the contents of your object database. Shall we look at the index?
Hang on. It's not the contents of the objects in the database. It's just a list of everything in the database.
Yes.
Okay. Right.
I like it when I can just say yes. So is anybody else unclear about that? It's basically like doing ls.git/objects, but also taking into account any packed objects. So what's in the index is just 2 entries. So main.cpp at 2 levels in the directory hierarchy.
Well, that's all the files in the index.
Yes.
But are there also things like potentially trees and things in there?
There are never trees in the index. Okay. There might possibly be a submodule reference.
Cool. Let's really not talk about submodules.
Good plan. I'm fully with you on that one. So anyway, let's turn this index into a tree. Here's my new tree.
Whoa.
Whoa. So as you can see, that tree is in that list of trees in alphabetical order. So that tree is this tree. And we've got quite a few kind of very similar looking trees. So if I have a look at this tree, which was it? A451 is the one that it's supposedly created. So this is my top level tree, which contains 2 entries now. A tree called A. Is the tree called A, or is the tree called 61D2AC8, and it's actually just like labeled A in this
directory called
directory? A. Okay, and then you can kind of like follow this down. Oh, except I think this is not going to work in an interesting way. Oh, no, that's right, yeah. And this tree contains another tree. And this is why I've got a whole lot of trees of size 28, because I've got a whole lot of single-letter file names. And then the other odd one out is the one that's got length
Top one?
35. 69 was my original blob, isn't it? So yeah, 35. I reckon this is going to be the lowest level one that's just got main.cc in it. So should we do it? Should we do that? Git ls tree. No, not that one. Oh yes, that one. Does that number look familiar to anyone, by the way?
Yeah, because it's identical to the one we had before, even though the one we've had before has now changed. So
yeah. So what we did earlier is we created main.ccc with this ID, and then we committed that at the top level of the repository. The tree that contains this one file at this thing has got this ID. And then, but you know, a directory containing this file, well, that's directory, what was it? How far did I go? G, H? I can't quite remember. But it's that directory's got exactly the same content. So even though the directory had a different name, well, the top level directory, is that just called slash in the Git repository? I don't know. So the directory's name isn't important. It's its contents that determine its identity. And that tree down at the bottom has got the same identity. So we shouldn't be surprised, although I was briefly there.
Okay, so we are sort of drawing towards the amount of time we should really take. We've been taking questions all the way through, so I feel like we can go over towards the hour-and-a-half mark rather than the hour mark. But I want to make sure if there are questions about any of the stuff we've got, or anyone is just totally lost, please ask before you run out of chance. Yes?
Maybe you can do this. I see how the commit relates to the tree and the tree relates to the file. But how does, you said log is a lightly sanitized version of the commit message. How does one commit relate to the previous commit?
Okay, so the question is, I see how the commit talks about the tree and the tree talks about the files and directories, but how is one commit related to the previous commit? Because that is obviously how the actual historical process of Git works. Thank you.
So when we made our original commit, there was no preceding commit, so we couldn't have a parent, so we didn't give it a parent. But now,
because parent just means the one before.
But now we do have a commit in our repository, so we could commit with this parent. What was the tree we created? This
right,
one.
Tree is. And by the way, we're making a commit here without actually having the thing that we're committing in the working tree, if I'm right.
Yeah.
So that chain of directories doesn't actually exist in the working tree. It's only represented.
On-disk file systems have really lousy performance. If you don't have to have the thing on disk, you don't need it. You can just like hash data as it comes in from the internet, write it into your object database, update the index just because that's slightly easier than dealing with raw trees and commit stuff, yeah.
Yeah, this is the way CB normally does his work.
So I've got another commit. Should I do that update ref thing? Oh yeah, here we go. Yeah, what's going on? So if I do that git cat file.
So you're familiar with how we manually make commits now, so this is easy, right? Yeah.
So this is another commit object, which is very much like the previous object, but there's one crucial difference is we have one parent. You can have as many parents as you want. What's the biggest one you've ever seen?
Not that many. I'm sure not as many as you.
There's one with 66 in the Linux kernel. 66 parents.
Nice.
It's the Kvolfu merge. So there are different classifications. It's no good classifying things too closely, but they're generally kind of like four-ish types of commits. So there's ones with no parents, which are like called root commits because they're kind of at the root of your repository. You can have multiple repeats in a repository because you can merge unrelated branches together. There are commits with one parent, which is just like normal commits. There are commits with two parents, which are generally called merge commits. And there are commits with greater than two parents, which are often sometimes called octopus merges. 8 is a very popular number of parents, but others are also available, like 66.
Yeah, it's highly recommended not to ever do that.
There's no reason not to.
Yeah, There's no reason in Git not to do that. There might be reasons for how you can ever possibly validate that any of those
if you're reviewing
changes are
a
correct.
66-way merge and you think that somebody didn't resolve the conflict particularly accurately,
Yeah.
okay, actually there is a bit of a secret. It's like normally if you do, if you commit something with more than 2 parents, and Git cannot automatically resolve the conflict, it will actually fall back to doing a number of 3-way merges. It never asks you, it never kind of calls kdiff3 and says, hey, and here are the other files that are involved in this merge. I don't know of any tools. Anyway, here's a challenge for you. Write a tool that does a 4 or 5-way merge correctly.
First, develop a human brain that can use that tool. Right, so let's see whether we can fit in another question, shall we?
Yeah.
Are we done with this?
That answered your.
Oh, yeah. Oh, yeah, okay. So the next question is, what does git reset do, and why does it do so many different things?
That's a good question. So git reset, just raw reset, basically makes your index match your head commit. So when we did write tree, we took the index and made a tree out of it. And the opposite of write tree is read tree, which is like the primitive version of reset. And read tree takes the index, or takes a tree and makes the index represent that tree kind of recursively. At least the single and 2 parameter versions of read tree.
Hang on, you're going to have to say that to me again. So git reset makes the index look like the working tree, is that what
No, make the index look like your head commit.
Okay.
So it reads the tree that's the root of that head commit into the index.
Okay, so it's just a way of saying, imagine I had done all this work without doing any git adds.
Yes.
Okay, that's git reset with no arguments.
Yeah. It has a number of knobs that you can twist. So if you do a git reset and you actually give it a commit ID, or even the ID of a tree, then rather than making your index look like your head, it'll make your index look like that particular commit instead.
And it will make your head be that commit, right?
And it will also update your head to point at that commit. Yes.
So that means it's as if I'd somehow earlier checkouted that commit, so switched to be working on that commit, and then done then made my working tree the way it looks now. Right?
But it won't change branches for you. So if you're on a branch, it'll actually move that branch to point to that commit. So it effectively dereferences that head link and then changes that branch to point at it, which is different from checkout, which moves you between branches. So that's the two things. So that's git reset with a parameter.
Is that a soft or a hard reset?
That's mixed reset.
Of course it is.
I'm glad you asked. There are other options. So I'm ignoring, for now, you can also give it a path parameter. Let's do that one later, maybe. You can do git reset -- soft, which does the bit about moving the, so soft, you need to give it some sort of a commit ID. Doing reset -- soft with no other arguments doesn't make any sense. So if you give it soft, it just does that head updating part. It doesn't actually change your index at all.
So it literally just changes that file called head inside .git to
it just
point
moves
at whatever you
your head.
told it to point at.
Yeah. So if that commit that you move to has got different set of files, then suddenly it'll look like you've staged the kind of the like undo of the difference between those two heads because
So
you haven't updated the index to match your destination.
So it's soft in the sense that it is changing where it thinks you are in history, but it's not changing your working tree at all.
And then there's hard, which is kind of like going the other direction to soft, which not only does the head moving and writing all of those, all of the tree of that new commit into your index, it'll also then change your working copy so it matches your index. So it basically is kind of like giving you a nice clean working tree which completely matches the index at this commit.
Yeah, so it's essentially forget everything I was doing and move to this point in history and make it look like I've not made any changes since that point in history,
Yeah.
right? So it's a bit
Yeah,
like,
I mean, reset and checkout, they're not the kind of like pinnacle of UI design, because you can also pass paths to reset, and then what it'll do is just make the index entries for those particular paths match either your head or a commit that you specified without touching the working tree.
so I'm trying to think of what's the difference between reset and checkout. In what way are they?
Okay,
do they
so
do a different thing?
There are two crucial differences with checkout and reset. So checkout with commit IDs will take you off the branch you're on and move you either onto another branch or onto a detached head state, whereas reset just moves your current branch around when you're doing with commits.
Okay.
When you're dealing with paths, and basically any scenario where you don't use ---- hard with reset, when you're using paths, reset doesn't touch the working tree, whereas checkout does touch the working tree.
And that's checkout's main job, is to make the working tree look like
I
something
hesitate
else.
to say main job when you've got a tool that has entirely two different jobs for two different scenarios. It's one of its main functions, yes. Again, checkout and reset, not the pinnacle of user interface design.
Sorry, you did explain git reset ---- mixed.
Yes.
Would you mind just saying that again?
So please explain what git reset ---- mixed means.
You know, I understand that, but I've never understood, really
No,
understood what
I didn't know it existed.
yeah, what that really does.
So soft means don't change my working tree, just go somewhere. Hard means go somewhere and change my working tree.
Okay, so we do actually have two commits, so we can kind of like demonstrate this. So what I've done in ultra quick time is basically like cleaned everything and got a good checkout of our top commit. So reset mixed. So if you remember, the top commit had our main.ccpp at the top level, and the second commit also had a main.ccpp at some kind of weird, nested directory. So if I did a ls-l now, a clean checkout of this thing has got lots of directories and a main.cc. Oh, I got all the way down to I, didn't I? So if I do git status, it's all clean. So if I reset to my parent, so what this is going to do is it's going to move the commit pointer to point at my parent and also update the index to match that new location, but it won't touch my working tree.
So just before you type that, just to explain what the carry symbol means. So head, if you say head, that means go and find the commit ID that's in this file called head. And if you use the carry, that means go and find the parent commit of that and go to that.
Yeah,
Where
that's
parent just means before.
Yeah, that's just because I temporarily forgot that 40-digit hex string.
Yeah.
So that worked fine, as you can tell by the utter lack of output.
Presumably that's printing out the commit ID.
And what you see now is I'm on master, so I haven't changed branches. I don't have anything staged because my index has been changed to match the destination head. But I do have this untracked directory called A.
Because my working tree wasn't changed.
Yeah.
Okay, so the index now looks like the previous, as it would have done in the previous commit.
Yeah, so that index is my
Yes.
initial commit where I just created my main.cc at the top level.
So in what sense is this mixed?
It's a bad name.
In what way is it different from both soft and hard?
So if I did hard,
It would change your working tree and that
Let's go
thing would
back
go
again.
away.
let's not explain this one for the time being. So I'm back in my state at the top commit, and I'm now going to do a reset hard. It's completely clean. Because that A, B, C, D directory with the single file in it was part of the commit that I was on, and I'm moving to a commit where that doesn't exist, and because it's clean, I don't have any changes. Actually, I did hard, so even if I did have changes, it would have got rid of it. It gets rid of the stuff that's no longer there, so I'm nice and clean. If I just do an ls on the file system, I've only got this one file. I don't have that directory anymore.
So reset minus hard just says, just forget everything, just go to this place, including my working tree. But what does mixed mean?
So mixed is just an identical meaning of no extra options at all. So when we just did reset, that's mixed.
So what's the difference between soft and mixed?
Okay, so here I am again. This time I've used a git reset hard to get here. So again, I'm clean the directory. I'm going to do a soft reset. I'll go to the parent again. So this is only going to move my commit, my head to point at that parent. So what's the difference? That the new head doesn't have that directory. However, it's not going to change my index at all. So because I had both files, the one at the top level and one all the way down, I should have something staged. So this is identically the change that the commit that I've kind of moved off has in it because of the parent relationship.
Okay, so I think I'm starting to come up with a summary. So git reset changes head, as in changes where I think I am in history. But it has these three different modes. It has hard, which changes the working tree to match that as well, and the index. It has soft, which doesn't do either of those things. And it has mixed, which changes the index, but not the working tree.
Yes.